All right, so in this video, we're going to start with revisiting the angle between two vectors, but now we're going to figure this out using cross products, which is actually less common, but it is kind of a nice result that then we can transfer into something else momentarily. So what we've got here is we've got two vectors. We've got v and w. We're going to cross them and get that perpendicular vector v cross w. We're going to try to find the angle between vectors v and w. And so to do this, the formula is sine theta equals the magnitude of v cross w divided by the magnitude v magnitude w. So it actually even looks somewhat similar, only again we're using the cross products now. The need for the magnitude is that we need to quantify so we get a number out of this, since the cross product itself is a vector. Now I'm going to set up the proof for this. We're not going to go through the whole thing, but I am going to set up the proof for it so you can see in fact that it is going to take us down the correct path. So for the proof, what I'm going to do first is actually just go ahead and multiply this over to the left side. So I'll have magnitude v, magnitude w, sine theta equals magnitude v cross w. And then I'll treat it more like an identity, to where I'm going to start on the left-hand side and try to make it look like the right-hand side. So magnitude v, magnitude w, sine theta. And this is the quote-unquote trick, and really the only trick in this proof. But we don't know anything about sine, but we do know some stuff about cosine. So I'm going to rewrite this as 1 minus cosine squared theta, and then since it's sine to the first, we'll have to put that square root on there. And then from here, I'm going to go ahead and write my cosine squared as my dot product. So that's going to be v dot w divided by magnitude v magnitude w, and that whole thing is squared. All right, so in my next step, as I clean this up, I'm going to do two things. First of all, that's squared and that's squared. All right, so because of that, that goes to the numerator and denominator. Then I'm also going to go ahead and create an LCD and put all this together. So when I do that now, I get magnitude v squared magnitude w squared minus v dot w all over magnitude v squared magnitude w squared. All right, so now the radical, we know, can go separately to the numerator and separately to the denominator. And when I do this now, fortunately, the v magnitude v squared will just become magnitude v. This will become magnitude w, and we'll do away with both of those. So that stuff goes away. And when all's said and done with this, what we have left is nothing more than magnitude v squared magnitude w squared minus v dot w, all underneath the radical. And at this point, this is where now you would start by saying let v equal v1, v2, v3, w equals w1, w2, w3, and then continue with these vectors performing these operations, and you should in fact come out with what this is. This is also probably a time to possibly start on the left and simplify it and meet somewhere in the middle, but I'll leave that for you guys. I just kind of wanted you to see how to get this thing started, because going from here to here is something that's, I wouldn't say obvious at the Calc 3 level to somebody that's seen this for the first time. So I definitely wanted you to see that, and then from there you could finish up the proof. All right, so now we're going to take that result that we started the proof of, and we're going to apply it to finding the area of this parallelogram. And so we've got two vectors, v and w, and I'm going to go ahead and extend out and up to actually create that parallelogram. Okay? So now, as I drop a perpendicular right here, if you remember, the area of a parallelogram is going to be base times height. So the base, maybe I'll write that out, the area is going to be base times height. And the base, that's just going to be the magnitude of v. That's going to be needing to quantify the length of this right here. And so then the height, that's going to be this guy here. And so if we call this guy theta, and we're interested in this, we can say that sine of theta equals the question mark over the magnitude of w. So that question mark is going to be the magnitude of w sine of theta. And we've done something similar when we talked about the scalar component for that projection vector a few videos ago. So our height is going to be the magnitude of w sine of theta. All right, now the magnitude of w sine of theta multiplied by the magnitude of v, that is, in fact, that formula that we just talked about a little while ago. That is the magnitude of v cross w. So the area of our parallelogram can be found by crossing v and w. And remember, that's all that's known. We're given two vectors, v and w. If we cross those two and find the magnitude, that's going to give us the area of that parallelogram. All right, so now we're ready to consider the parallelepiped. Parallelepiped, so the three-dimensional parallelogram. And we say spanned by u, v, and w. Span just means created. And much like the last one, we're going to assume we only have these three vectors, and that is, in fact, then going to create this three-dimensional solid where we've got our v, our w, and our u. So we've got our three vectors here, and those three alone are going to allow us to create the rest of this space here. So if we compute the volume of this, so volume, just like other three-dimensional objects, it's going to be area of the base times the height. Well, the area of the base, that's just going to be the parallelogram right here. And so we just did that a moment ago. That's going to be magnitude v cross w, right? So the base is created by the v and the w. And so the height, this is where we're really going to have to think a little bit. So the height of this thing is going to be found by using this vector here, and our height is going to cut us off right there. So that's what we're trying to find. Well, that vector, that's going to be our v cross w. Okay, that's going to be the one perpendicular to both v and w, but then I need to rescale it, okay? So what I'm looking to do now is I'm looking to find the scalar component of this guy right here. So I need the scalar component of that vector right there to give us the height. And that scalar component is the same one that we found or worked with in an earlier section, but now, of course, we just have different vectors. So we're going to have, following that formula, u dot v cross w divided by the magnitude of v cross w. And so again, I would encourage you to go back and look at that formula and see how it relates to the vectors we have now, the u vector and the vector v cross w. So that's all that is, the scalar component from the other day. Now, we put all this together. The volume is going to be magnitude v cross w, and then we'll have this u dot v cross w over magnitude v cross w, in which case these go away, leaving us with the volume of a parallelepiped as u dot v cross w. So there's the area of the volume of a parallelepiped, which is pretty convenient because remember, again, all we have to start are the three vectors. We don't need anything beyond it to find the actual volume, though. All right, the last thing I want to mention, excuse me, is a triple scalar product. And it is on page 726. I would encourage you guys to take a look at that. It gives you a pretty fast way to compute this guy right here. And so I would encourage you to take a look at that. There will be an upcoming assignment where I ask you to not use it on a certain problem. But for the most part, if you have a case like this and you want to save a little time, the scalar triple product will help you do so.